Okay, this is work with Ivan Korotkin, who's also in Southampton, and it's on energy in the DFN model. So the motivation really comes from the Doyle-Fuller-Newman model, which is a very versatile model, and if it's properly calibrated, gives extremely good agreement to current voltage data. And so if you listen to Ivan Korotkin's talk, he's going to talk about some work he's done with Alana Zolka in Lancaster. Alana's parameterized cells, and then Ivan has used the parameterization in the model and shown that there's very small discrepancy between the predictions of the DFN model and the experimental results. Furthermore, as everybody knows, batteries are energy storage devices, and therefore you'd like to know where the energy goes, and in particular where it's wasted. But there's currently no systematic way of accounting for energy dissipation using the Doyle-Fuller-Newman model. That's not to say that people don't model heat production using Doyle-Fuller-Newman, but the way they do that, and there are many works that do this, none of the formulae that they use are actually consistent with overall energy conservation. So the idea of this work here is to derive an energy conservation law from the Doyle-Fuller-Newman model, and then use that law to obtain expressions for the heat production which are consistent with conservation of energy. But not only to do that, but to use the law to investigate where there are sources of significant energy loss in the battery, and therefore as a tool to improve cell design. So the energy conservation law is going to be couched in terms of the Gibbs free energy of the device, and it turns out that there's a natural Gibbs free energy that's associated, that you can associate with the Doyle-Fuller-Newman model, and this formula here is what that Gibbs free energy looks like. Essentially, there are three parts to it. There's the Gibbs free energy associated with the chemical energy in the anode particles. That's this first term. The second term is the same thing but in the cathode particles, and the final term is the chemical energy associated with the electrolyte. So here, if I look at the first term, what you're doing here is integrating an energy density, which is curly GA, over the volume of the particle, and then summing all the particles in the electrode. This second integral in X sums all the particle in the electrode, and it gives you the Gibbs free energy per unit area of the cell. Normally you'd expect the Gibbs free energy just to be a function of time, but however you also ought to worry about temperature as well, because we know that the energy densities in the electrode particles are temperature dependent. So the energy densities are given by these formulae here. So these are just integrals of the chemical potentials in the different parts of the cell. So the chemical potential, for example, in the anode is minus Faraday's constant times by UA, and that where UA is the open circuit voltage. Other things to say, the curly ends and are particle densities, the anode and cathode, and the epsilon L is the volume fraction occupied by the electrolyte. So it turns out that if you go back to the Doyle-Fuller-Newman equations and you do lots of integrating by parts and make use of the internal boundary conditions, you can demonstrate that this energy conservation law is a consequence of the Doyle-Fuller-Newman model. So here you see on the left hand side, this is the rate of change of the Gibbs free energy of the cell minus the rate of change of Gibbs free energy of the cell is equal to the power output of the cell plus a load of energy loss terms, irreversible energy loss terms, which are associated with irreversible heating. So this first term is the irreversible energy loss in the electrolyte. The second one is the energy loss associated with heat of mixing in the anode particles. This is ohmic losses in the binder conductivity additive matrix, and this one here is the polarization loss across the interfaces between the electrode particles and the electrolyte. And then these are what these various terms look like. And if you go and compare that to what people write down for the irreversible energy losses for the Doyle-Fuller-Newman model, you see that these bottom four terms are actually identical to what people will write down. The term in the electrolyte is slightly different. In particular, there's an extra term in here, and then most people will neglect the heat of mixing in the electrode particles, and that turns out to be rather a bad approximation, because often the heat of mixing in the electrode particles is very significant. I should just mention this paper by Lass and Sausch. They've looked at this problem in a different context, so not in the context of Doyle-Fuller-Newman, and they've arrived at irreversible energy losses in a lithium-ion battery that look rather similar to this, using entirely thermodynamic arguments. So, having derived this energy conservation law, we want to validate it, and Ivan has done this in Dandelion, and what he's done is he's integrated the left-hand side with respect to time and compared that to the integral of the right-hand side with respect to time. And he's done this for a cell that's been parameterized by Acker in 2013. He's done it for various discharges. He's done it for a 5C discharge and also for a drive cycle. And here you see the integral of the left-hand side is given by the black curve, and the integral of the right-hand side is given by the yellow dash curve, and they lie exactly on top of one another. And that's true both for the 5C discharge and for the drive cycle. And furthermore, you can show that the error tends to zero as you refine your mesh, your solution mesh for the Doyle-Fuller-Newman model. So given that we now have confidence in this law, the question is, what can you show with it? And in order to illustrate some of the things that happen, again, this is some computations performed by Ivan. He split up the energy dissipation terms to show the relative magnitude of these dissipation terms, and these are integrals over time as well. And so here this red curve illustrates the energy dissipation due to the heat of mixing, and in a 5C discharge, this is actually the dominant source of energy dissipation, and it's something that nearly everybody neglects, so that's slightly surprising. In a 10C discharge, it turns out the dominant source of dissipation actually comes from the electrolyte, and then this is in a non-uniform drive cycle. In this case, for our drive cycle, the dominant source of dissipation comes from polarization losses on the edges of the cathode particle. So one more thing I just want to very briefly mention is you can also use this formalism to account for reversible heating, and in order to do that, you have to relate the Gibbs free energy energy conservation law to the enthalpy, and you find the following expression, that the one at the bottom is the expression for the reversible heating, which is slightly different to the one that's generally used, but the two turn out to be the same if you assume that the concentration in the particles, the lithium concentration in the particles, is uniform. In other words, there's no spatial gradient inside a particle. So in conclusion, the accuracy of the Doyle-Fuller-Newman model predictions justify computing exact expressions for energy dissipation, and we've derived a mathematically rigorous result which shows that if you have the Doyle-Fuller-Newman equations, they imply this energy conservation law. And I think this is a kind of helpful way about thinking about how batteries operate, is to think in terms of where the energy dissipation occurs, because it allows you to see where losses are occurring, and then it gives insight into how you can improve the design of the battery. And therefore, I think it's a sensible route to build design optimization algorithms. And it also highlights that significant heat production terms are being neglected in standard approaches to battery heating, in particular the heat of mixing and electrode particles. And I think I'll finish there.